Hello, everyone. My name is Jan de Geer. I'm the director of Matrix, which is Australia's residential research institute for the mathematical sciences. And today we're very pleased to host Dr. Marcy Robertson from the University of Melbourne, who will give a public lecture on mathematical oranges in deep space communication. Before we start, I want to say a little bit about Marcy. Marcy is a senior lecturer and ARC Future Fellow at the University of Melbourne. She obtained a PhD in 2010 at the University of Illinois in Chicago and was a postdoc at UCLA before moving to Melbourne in 2015. Marcy's research is in algebraic topology, and she looks at things called infinity operads, props, and related structures with applications to low-dimensional topology and geometry. Today, she will speak about packings of balls and oranges and how that relates to deep space communication. And I'd like to welcome Marcy and hope you'll enjoy the lecture.
Well, thanks everyone. So bear with me real quick. There is a quick arrangement of screen sharings that have to happen here. And then stop share, reshare. Gorgeous. All right. So thanks. So right. So when Jan and the team at Matrix asked me about giving a talk for National Science Week, I was trying to think about what are the topics that I learned when I was younger that got me excited about having a career in math. And one of my first loves in life was astronomy. This way you got these little things. And I love thinking about and tearing open my science magazines and looking at pictures from space. But something occurred to me at a certain point is, how do we get pictures from space? They're not exactly sending film down. And how do I know that these are accurate? Right? Is this really what Saturn looks like? So these two pictures here, these are from the Voyager 1 probe in the 70s. Some of the first color photos that we ever saw of the planets in space from NASA. And I wanted to think about, I wanted to tell you how exactly this worked. Right? So I would learn about how these, I learned about how these photos were transmitted. And it's actually led me to how beautiful mathematics can be. Right? So let's start with a really basic idea for our conversation, which is, how do I encode a digital picture? Right. So if I take a digital picture, we know that these are transmitted as a series of words, which are written in binary code. So a sequence of zeros and ones. So this means we are going to break down our picture into squares called pixels. So these little boxes are a pixel, and assign to every pixel a code word, which is written in terms of ones and zeros. So for this first example, let's decide that our code word for a white square will be a 0, and our code word for a black square will be a 1. So here I've encoded this picture, this rather crude picture of a cat. Okay? And if I wanted to transmit this picture to a friend, I would send them a series of words in 0 and 1. So I would send 0, 1, 1, 0, 0, 0, 0, 0, etc. Reading from left to right in blocks, and my friend would know, okay, I am getting white, black, black, white, and so forth. So in the case that we have perfect transmission, my code goes directly through to my friend, that is, no data gets confused, then this is good enough code to send this black and white image of a cat. Right? Nothing needs to be done here. But now, if we want to really think about how nothing in life is perfect, and we want to be able to account for noise in our line, right? So noise, we have our source, our picture of a cat. We have our transmission, which is whatever I'm using to send my zeros and ones. And then you have your receiver, and then what you've decoded from the receiver. And in the middle is something called noise. So in the signal, that means that noise just means some way of zeros flipping to ones or ones flipping to zeros, some kind of interference. So in order to fix this and see here, my cat's ear has been chopped off because I might have said 0, 1, 1, 0, 0, but you might hear 0, 0, 0, 0. And this leads to distorted images. There you go. So the first thing we can do is increase the number of bits in our word. So bits, I mean the entries in our words. So we make our code words more complicated, so it's easier to detect errors. Okay? So to do this in our example for this black and white cat, let's increase the number of bits in our code word for white. Let's now say it's 0, 0. And let's increase the number of code words, or the number of bits in our code word for black. Let's call that 1, 1. So now when I transmit my image to my friend, I'm going to send 0, 0 for each one of the white squares and 1, 1 for each of the black squares. So my friend will receive a series of 2-bit words, and they have the choice of what they can receive. They can receive 0, 0, 0, 1, 1, 0, or 1, 1. These are all possible 2-bit words that they could have. Now, if you receive either a 0, 1 or a 1, 0, you're going to know that something happened along transmission. Some noise in our transmission line caused an error because 0, 1 is not a valid code word, and neither is 1, 0. So this is an example of what's called 2-bit one error detecting code, because each word is 2 bits long, so two digits here long, and I can detect a single error, which is that either one of these zeros flipped to a 1 or a 1 flipped to a 0. Okay, but I cannot tell you where the error came from. I don't know if this 0, 1 came from flipping the first 1 to 0 or the second 0 to 1. And I can't tell you if this 1, 0 came from flipping the second, this 1 to a 0 or this 0 to a 1, right? So I know there's an error and I can radio back to my friend and ask for clarification, but I can't correct the error without contacting my source again. All right. So I want to improve a little bit farther, and I'm just going to keep adding bits to my word. And you can see how this makes it easier. So let's improve by adding a 3rd bit now to our word. So this means my code for white will be 0, 0, 0, and my code for black will be 1, 1, 1. So now when I transmit my image of the cat, I'll do a series of 3-bit words, 0, 0, 0 for every white square, 1, 1, 1 for every black square. Now they're going to receive a series of words, which could be any of the following 8 words, right? I can have 0, 0, 0, 0, 1, 0, and so forth. Now, if my friend receives 0, 0, 1, that is most likely going to be the code word for white, 0, 0, 0, because there's one small error, right? One of the bits flipped to 1. So we could think about this as being close to white and correct our code. But if I flipped 2 bits, if I end up at 0, 1, 1, oops, that's not supposed to click, that's what happens. If I ended up at 0, 1, 1, right, I can't necessarily say that this could be corrected to white because it's too far away somehow. There's too much information, and it's closer to 1, 1, 1. It's closer to the code for black. So it seems like it's more likely that 0, 1, 1 would be corrected to black. So what I'm demonstrating here is a code where each word is 3 bits long, and where I can detect an error if a word differs from my code by 2 bits. So I know this is an error. I know this is an error. But I can correct the error if I know that the word differs only by 1 bit. So 0, 1, 0, looks like I just flipped this middle 0 to a 1. I can correct this to white. To formalize what I'm doing to make this make sense, let's think a bit about what it means for when I said that a corrupted word is close enough or far enough from a code word to be corrected. So we want to think about our words as being points in space, and the bits are giving me directions to that point. So using the example of our 2-bit code, I'm going to take this literally and say that the code 0, 0 that gives me white, I'm going to place a white dot at the point 0, 0 in the XY plane. And I'm going to take the point 1, 1 that gives me a black square. I'm going to put a black dot right at coordinates 1, 1 in the XY plane. I can also plot my bad points. So where I flipped a bit, so here I'll do 0, 1. I put a gray dot there because it's ambiguous. And here I have 1, 0, and I put another gray dot there. And that's one of our bad points. So we're thinking about this, and I've said now in looking at it like this, each of my bad points, these gray dots, are precisely distance 1 from my good points. So this is, distance 1 from the black dot and distance 1 from the white dot. And looking at it in this depiction, this allows us to clarify what I mean when I say we cannot correct the errors in this code. All of the bad points are precisely the same distance from all of the good points. So I can't really say that one is closer to a white dot or a black dot. For the mathematicians in the audience, I'm just going to say that what I'm really doing here is I'm saying that my 2-bit words are vectors in a 2-dimensional vector space over F2. So as we continue to go up in dimension by adding an extra bit, so every bit I add, I'm going to be saying is going up in dimension. I want to think about what's going on and define the notion of distance. I want to define something that's close enough. So I'm going to define something called the Hamming distance, which is how many bits were flipped. So here, if I start at 0, 0, 0, my code for white, and I flip 1 bit to get 1, 0, 0, I want this to be distance 1 from my original code word. And if I flip an additional bit to get 1, 1, 0, I want this to be distance 2 because I flipped 2 bits. And the total distance from 0, 0, 0 to 1, 1, 1 going any direction in this cube is 3. So the distance between my code words is 3. This is a notion of Hamming distance, or a metric, gives me a metric, and it allows us to use geometry to determine if a code can be corrected. So to be a bit explicit, I'm saying that a code can correct up to k errors. A code is k error detecting. So I can detect if I have up to k number of errors, if the minimum distance between 2 code words is at least k plus 1. I can say that a code can correct up to k errors if the minimum distance between 2 code words is at least 2k plus 1. So in our example, the distance between 0, 0, 0 and 1, 1, 1, between white and black, is 3. So I can detect 2 errors, 2 plus 1 gives me 3, and I can correct 1 error because 2 times 1 plus 1 is 3. All right. And this generalizes quite drastically. So what I want to do is like make this a bit more clear. And so let's think about using our Hamming distance by drawing the code words as the center of various spheres. Okay, so just to recall for ourselves, so a sphere, just in general, is a collection of points all equally distant from a chosen center. And in symbols, an n-dimensional sphere of radius r, so centered at x, so the n-dimensional sphere centered at x are the points y, which are a distance, so the distance of y is less than or equal to r. So everything contained in some radius. All right. So the Hamming sphere of radius r around a code word is the collection of points which differ from x by at most r flipped bits. So I'm drawing here, so if I imagine here I have my code word 0, 0, 0, then in this gray radius, this would be radius 1, these are the things that were flipped by 1 bit, which I can correct. And in the next radius, these are the ones that I know were detectable, but I can't correct errors. So like 1, 1, 0 in my example earlier. So this is a radius 2. And the centers don't intersect because they're distance 3 apart. So our goal when writing good code, right, is that we want to be able to pull the code words apart in this, think about them arranged as spheres. We want to pull them apart so that there are no ambiguous words, because the farther apart our code words are, the less likely it is that one message will get mistaken for another. But this can also become highly inefficient. If our code words are too far apart, we're just wasting computing power to account for errors that are unlikely to be a problem. So the goal is to find the best possible answer, to pull the spheres apart so they don't overlap, but to put them close enough together so that they we don't waste any energy trying to correct or detect errors. And this is an example of what's called a sphere packing problem. Okay. So the idea of sphere packing is about trying to find the most efficient way to fill a space with non-overlapping spheres. So as a warm-up, we're going to look at how this works in two-dimensional space. In our picture here, I've got an arrangement of two-dimensional spheres, which are circles, in the two-dimensional space, in the plane. So we think about this sphere packing as a tiling of the plane by circles. All right, so one way to think about this also is to imagine trying to cover a table with coins. So in this arrangement, I have aligned the circles. I stacked one on top of the other so that the circles, so the centers of the circles are in a line, right? And this is called a square arrangement of circles because if we connect the centers of the circles, we have a square. And these little gaps here, these inefficiencies in our code are the inefficiencies in any code, right? So if these were code words, this could be the error correcting circle around it. And this gap here is some inefficiency I'd like to fill. So in order to see how efficient this, this packing, this arrangement is, we can zoom in on this square over here. And notice that we can compute now what part of the square is not covered by circles. Okay. So to do this precisely, we'll say the density of the packing is the area of the square covered by circles, so now shaded in blue, divided by the area of the square. So now you can look at those formulas that you learned in class that you thought you'd never have to use again. So if our circle has radius r, this means that the square has side length 2r, right? This is the circle center. So this is side 2r. And the area of the square is then 2r squared. If each of the 4 vertices here are covered by a fourth of the circle, and the area of a circle is pi r squared, we have 4 times 1/4 pi r squared on the top, which reduces to pi over 4, or about 0.785. This means that the percentage of our square covered is about 78.5%. So this is how effective we are at filling this space. This means our arrangement of circles is 78.5% effective at filling the space. So can we do any better than that? Most of you probably already had an idea in your head when I put up that first picture about how we could do better. Right? We can align the rows of circles so that we try to fill in the gaps left here, right? So we want to first line up the circles so that the centers form a straight line. And then the next row, we'll try to sit them in the gaps. In this arrangement, if you start drawing lines from the center of the circles to one another, you'll notice that these are arranged as a hexagon. Each circle is surrounded by 6 other circles. Okay, and this is called a hexagonal packing because of the hexagon shape. So now, as before, we can look at how efficient is this thing? How efficient is our code if this is how we're going to be sending it or performing it? So we zoom in on our hexagon, and the density of our packing, so this is going to be the portion of the hexagon covered by circles over the area of the hexagon. Okay? So we can look at the number of circles here. If you add them up, we end up with 3 full circles covering this hexagon. So that's 3 pi r squared. And on the bottom, well, I calculate the area of the hexagon by realizing by not clicking, by realizing the hexagon can be covered by a bunch of equilateral triangles, right? 6 of them. And when you work all of this out, you'll notice that this comes down to pi over 2 root 3, or approximately 0.907, which means that the hexagon is around 90.7% covered by circles. So our intuition is correct. This is a more efficient way to fill the space with circles, and significantly more than the previous one. And in fact, this is the most efficient way of packing circles into space. But proving it isn't easy, actually surprisingly hard, and to do so, I won't be able to do that tonight, but let me give you some idea about how we think about proofs like this, because this will come up later. And if a lot of this sounds like gibberish, don't worry, you're going to see more and more pictures as we go up dimensions. So the notion, what's happening here when I'm looking at the shape formed by the circles, by the centers of the circles, is I'm looking at the underlying lattice of the packing. So a lattice is a collection of points in space with a well-defined relation between them. So here I'm thinking of these are just evenly spaced points, and the relation goes between them. Okay, so formally, a lattice is in n-dimensional space is a discrete subgroup of rank n. But you can think about these as being just evenly spaced points with some pattern and relation between them. Now, if we have a really nice lattice and we can translate from one point to a next, I won't really be able to explain, but if you do a translation of the plane and points of the lattice end up on the next one, then this is called translationally invariant. And so when I can think about this becomes a sphere packing. So what I do is if I have a nice lattice, so here, this is a picture of a translationally invariant one. There's no black squares. And here I'm saying that if I deformed the space, did a linear transformation for the students in the back, that I don't preserve my lattice, the points change, okay? If I have a nice lattice, then I can arrange spheres on my lattice where the center of the sphere is at the lattice points. And in that case, I have the sphere packing, and I can say that the density of a lattice packing is the proportion of the polytope, so the shapes, covered by the circles over the volume of the polytope. So we're thinking about this in any dimension. So just like we did in the previous slide, where if I have this hexagon, I have the portion of the hexagon covered by circles over the area of the hexagon. It's area because we're in 2D. Now, not every lattice gives you sphere packings, and not every sphere packing comes from a lattice. It's just a special thing, and we'll see that it comes up later. Okay. So let's test our intuition now. So as we go up dimensions, right, with our two-dimensional thing, I don't think I told you anything that surprised you. You know to arrange these circles so that you fill in gaps, and it acts the way you want, right? You just shove oranges together. And 3 dimensions, our intuition is also pretty good. So if we now want to stack 3-dimensional spheres or oranges, we can think about using what we know from 2D as a basis of this. So here, the first layer, so if I want to pack some oranges into a crate, I'm going to start with the first layer, and I'm going to use what I know about 2-dimensional sphere packing to do the hexagonal arrangement. So what I mean is I want to think about if I project or to put the shadow, I want to have the same hexagonal arrangement here. Okay, so I'm using something from the lower dimensions, and that's what this little animation is doing. I'm thinking of these black dots as the sort of like shadow of the orange right here. So the second layer, well, you're going to plop your spheres into the holes in between them, right? We're just going to try to fill the gaps left by the previous layer. But now, at the third layer, we actually have some choices, okay? So this is 2 layers. Here I have the blue is layer 1, purple is layer 2. So one choice we could have is to line up the third layer with the first. Okay, so we could just try to make sure the center of the third layer of the spheres lines up directly over the first layer. This leaves little gaps between the spheres, and if you look really closely, I'm not sure how well this shows up on your screen, the little gaps that are left over are in the shape of hexagons. This type of arrangement is therefore called a hexagonal close packing of 3-dimensional spheres. You can also see this if you sort of slice through this packing, you can see what they look like. And these are the types of arrangements we see a lot in studying chemical arrangements of atoms and materials. So hexagonal arrangements of atoms are known to be in titanium and zinc, lots of crystals. And if we compute the volume, the ratio of the volume of these spheres over one of these sliced hexagons, we get a density of around 74%. Okay, so that's good, but not great. Right. And our other choice for our third layer is to fill in all the gaps. So now I have the blue layer is my first one. Then I put the purple layer on top. And then wherever those gaps were, I now put the green oranges on top, right? The third layer goes there. This is called a cubic close packing because if you slice it open, it looks like this cube arrangement inside. And this is the way it looks when we look at the centers of the spheres. So this type of arrangement also is very common in nature. This is like atomic arrangement for metals such as gold and silver. And what do you know? This cubic close packing also gives you a density of 74%. And in fact, there are actually an infinite number of ways you can keep doing this. And if you study chemistry and crystals, you'll see a lot of them. But these are the best you can do, in fact. So this was sort of known. It's known to since the time of Kepler, but it was proved by Hales in 1998, and the proof is extremely complicated using a lot of computer code. So this is the best we can do. But that's a bit weird. Right? Why is the packing in higher dimensions less effective than in lower dimensions? Right? In dimension 2, we were able to find a hexagonal packing with an efficiency of more than 90%. But in dimension 3, the best we could do is 74%. And this is happening because spheres shrink as you go up in dimension. So let's think about this. Let's look at the circle in 2D. So if we look at the circle inscribed in the unit square, so this is the, I'm thinking about it as just barely touching each side. Well, the circle covers a little over 78% of the square. So if you look at the area of the circle over the area of the square, you get again around pi over 4. But this doesn't, if you go to 3 dimensions, and now I inscribe a sphere inside of a cube, where it's touching each side of the cube. Well, the volume of the sphere, which is 4/3 pi r cubed, over the volume of the cube, 2r cubed, is around pi over 6. But that means that the sphere is only taking up about 52% of the volume of the cube. And in fact, this trend continues as your dimensions increase, right? So if we add a 4th dimension, the circle, the sphere will get even smaller. And for inside any n-dimensional cube, if I draw a sphere, an n-dimensional sphere inside the cube so that it touches all 2 n sides, this is actually going towards 0 as n gets larger. Right. So as we go up, we tend toward very, very small. And in fact, higher dimensional spheres become, for lack of a better word, spiky. They look very strange. So higher dimensional spheres also are called hyperspheres if you need to Google. And at the last slide, I have some videos for you. So as an example, if I take the dimension 30 and I compute the volume of the sphere, and then I take that over the volume of the 30-dimensional cube, I'll find that the sphere has 10 to the minus 13th, 13th the volume. I don't know how to say that, but 0.00 blah, 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 1, the volume of the cube. Okay. So to think about this analogy, I tried to, you could think about the sphere being the size of a grain of sand, and we plug it into a cube the size of the MCG, except for what's weird about what's happening is that the grain of sand would somehow be touching all the sides of the stadium. Okay, so it's very thin and spiky. This is a basketball court because they don't have graphics for square cricket grounds. So what happens with these higher dimensional spheres is that our intuition is breaking down completely, right? So we can no longer think, I understand how to arrange pennies on the table, I understand how to stack oranges. If I have higher dimensional objects, I'm not going to be able to use my intuition. And in fact, we generally don't know much about how higher dimensional sphere packing works at all. But something really strange happens in dimensions 8 and 24. In dimensions 8 and 24, whenever you, the sphere shrinks so much that there's enough space to shove another sphere in between each one. So they're somehow like perfectly described. So as I said, our intuition is, we know almost nothing about what happens. And I don't mean we can't prove things. I mean, we literally have no idea. So, but in dimension 8 and 24, we actually can go back to this notion of a lattice, right? So remembering what I'm thinking about is the lattice is, so I have some points arranged in my n-dimensional space, and they have a relation between them. Right? So I'm thinking of, here's a point in my lattice, here's a point in my lattice. These lines are giving me a relation between them. Okay. And so since we can't picture our higher dimensional spheres, although there's some interesting videos online about this, we're going to rely on what we know about lattices to think about how to tile high dimensional space by spheres, by polytopes, right? So we said that a lattice gives you a tiling of the space. So here, what I mean by tiling, again, this looks like, we think of bathroom tiles. This is a square lattice, and I'm literally tiling two-dimensional space. So in dimension 8 and 24, we have two special ones. Let's go into it. Cool pictures are coming. All right. So let's see if I can play this without it being weird. All right. So what happens in E8? So E8 is an exceptional object in math, and it arises in all kinds of different fields. So in group theory, and physics and topology, you're going to see this weird lattice come up. And it's hard to show what it looks like. This is a construction of it happening in this video over here. But we know that E8 tiles 8-dimensional space. So it covers 8-dimensional space in the same way that these squares are covering 2-dimensional space. So think of it as it's giving me like a bathroom tile covering of whatever 8-dimensional space is. And this is a really interesting lattice because each point in the lattice is exactly the square root of 2 distance apart from from another point. So this tells me how I could make a sphere packing. I can simply surround each point by a sphere of radius √2/2. And so that's a way we would just take, we have a lattice, we know something about the distance between the points, we're just going to shove a sphere around each point in the lattice. And when we compute, we check the density of this packing. This is approximately 25, little over 25% dense. So that means we're covering about 25% of 8-dimensional space with 8-dimensional spheres, centered at the E8 lattice points of radius √2/2. So this is much less dense than lower dimensions. But it turns out this is actually the absolute best we can do. So Maryna, and I should have looked up how to pronounce her last name before this talk. So I'll just say Maryna, yeah, I'm not going to go with it. It showed that this is actually the best possible sphere packing in dimension 8 in 2016. And this is actually the paper that won her the Fields Medal this year in 2022. And that's a picture of her. Oh, this is also a picture of the E8 lattice, sort of graphically. All right. But wait, I promised you I would talk about codes. So in 24, something is kind of interesting. So in 1971, there was a paper in computer science or information theory written by Leach and Sloan, which showed that you could use sphere packing built from we can use a sphere packing built off of a 24-dimensional lattice, which we now call the Leach lattice, to produce a 24-bit error-correcting code called the Golay code. So this is a special lattice. Here's a picture that I got. This is from the original paper. And there's lots of interesting videos about constructing this lattice. And this code encodes 12 bits, so 12-digit long code words, right? So now if I was in Golay code and I wanted to use my same code, I would have a string of 12 zeros for white and a string of 12 ones for black. And in 24-bit sequences, so I'm going to take my 12-digit code word, I'm going to add 12 extra digits on the back end so that I have a way to error correct. And this detects any 3-bit errors, so up to 3 flips. It detects up to 7-bit errors, so 7 flips can be detected, and we can correct up to 3 bits. So, oops. So you can correct up to 3 bits. And this is the exact code they used to transmit the pictures from the Voyager spacecraft. So this was in 71. This sort of thing was happening in the 70s. And what happens is you use different strings of zeros and ones to encode colors. So like 1, 0, 0, 1, blah, blah, blah for red, 1, 1, 0, 0 for green. And so this is giving you each pixel in color. Okay. And this, so there's some fuzziness, but that's basically where we're going with it. Okay. And in fact, the sphere packing built in this paper in 1971 based on this lattice, which is actually quite nice to construct. It's not as fancy as you might think. This is the best we can do as well. So in fact, building on the dimension 8 proof, Maryna Viazovska, I'm going to say it's so wrong, someone can please correct me later, and a team of other mathematicians, they actually showed that the sphere packing based on the Leech lattice is the best we can do. So what's really interesting and what I wanted to point out is that nobody expects that the techniques from dimension 8 and 24 will generalize to other dimensions. So we don't even really know, we saw the dimension 2 and 3, we can prove those, and those match our intuition. We know dimension 8 and 24, but I don't know anything about dimension 7. And at one level, we don't really know why this is the case, although it's not uncommon. So nobody has been able to find a proof or even a really heuristic argument that rules out similar phenomenon in higher dimensions. But the special role of 8 and 24 aligns with a lot of experience in math. Math is full of what are called exceptional or sporadic phenomenon. They occur in only finitely many cases. And both the E8 and Leech lattices are examples of exceptional and sporadic phenomena. So it's really quite remarkable. But if we're going to do more sphere packing and different codes, we're going to probably need completely different techniques for proof and for constructing them. All right, I will stop there. I'm sorry, that was my time. And I put a list here and I can put these in the chat. If you want to learn more, I have some resources for mathematicians who want to actually, there's a really good article in the notices. And if you want to have some real interesting work on trying to understand what higher dimensional spheres look like, as opposed to these spiky things I have there, and etc. Right, I will stop there. Thank you.
Well, thanks very much, Marcy. So on behalf of everyone here, I'll applaud. And you get some reactions on screen. That was a very beautiful talk about sphere packings and how it relates to practical applications in deep space communication. As you saw in the chat, you can ask questions to Marcy via the Q&A function at the bottom of your screen. And if you put them in, we'll invite you into the meeting and you can ask your question in person. And the first 2 questions are by Nalin Hitva. So Nalin, you should get an invitation to join, and then you can ask your question in person. Okay, we can hear you now. Nalin?
Yeah. Can you see me or hear me?
We can hear you.
We can hear you, yeah.
I know the definition of a group and a subgroup, but may I know what is the meaning of a discrete group?
Yeah, so what I meant here is that the each point is isolated point in space. So R is a topological group. So I'm thinking of the real numbers as having both a multiplication, but that it's continuous. And here I want this to be a lattice to be discrete in the sense that there's no other points of the lattice within a ball of the lattice. So where I have
may I interrupt? Sorry to interrupt. In fact,
Mhm.
You mean discrete topology?
I do, yeah.
Yeah. Okay. Understood. I have another little question. Yeah. Since you spoke of used the word tiling and dimension, could you please throw some light on the connection between what you are discussing now and the very basic tiling theorem in topology?
Which tiling theorem in topology are you
I
thinking of?
think it is related to the concept of dimension. If we cover an n-dimensional cube with finitely many closed subsets, or of arbitrary shape, then there are exactly n+1 points at which these, which are contained in these subsets also. I think I fail to recollect the correct words.
Well, so I
But
think
for the two-dimensional case, I do remember, if we divide a country into various provinces, finitely many provinces, they may be arbitrarily shaped or not even connected, then there are exactly 3 points at which all these provinces meet. Yeah, I know the two-dimensional case of this tiling theorem.
yeah, so that makes that is closely related, right? So let me see if I can find the picture of the square tiling. This is a good example. So here, right, if you're thinking about what that's saying is how right, so if we're dividing an area into a bunch of even pieces, right, that at least let's see, then some number of points, if I remember correctly, this is like a Lebesgue thing, but at least n of the n+1 points belong to the same region. So this is talking about how close together tilings are. And so you can use similar things like to this to talk about when you have a sort of maximally dense lattice in space. But I don't know which dimensions that works in. I think maybe all of them. But
Okay.
so it is closely related, but I'm not, there's a lot of things that people call the tiling theorem, so I hope I'm not telling you the wrong one.
No, it does illuminate, throw some light. My question itself was a little bit vague, I noted. I have one more question, may I ask?
Well, maybe we can first go to someone else and keep your question in reserve.
Sure.
Keep your question in reserve, and we might come back to you.
Yeah.
Next question is by Peter Price. Peter will invite you to ask it verbally. Okay, you're in the meeting, Peter. But you have to unmute.
Thanks. As I understand it, there's 2 or 3 equally special 16-dimensional lattices, even unimodular lattices, and there's 23 other special 24-dimensional lattices, if I remember correctly, besides the Leitz lattice, one of which is 3 lots of E8. Is anything known about the packing density for these other special lattices? Apart from not being as good as the Leitz lattice?
It's interesting, they don't, and not that I'm aware of. I mean, so I know that in 24, we know that none of the other lattices sort of give you as dense of a packing, but it doesn't use as far as I know, that the Leech lattice is like uniquely unimodular or something like that. So I know E8 is unique unimodular one in dimension 8, but that's actually not used in the proof. What is used is a certain property of symmetry of the lattices that gives you this like Poisson summing formula that so it's somehow like I actually thought when I first heard about this proof that it would be the fact that these were unimodular and even and like really nice lattices that they were using this to prove it, but it's some other formula generated generated by sort of what are these called? These Poisson summing formulas, and it doesn't appear that the same thing will work in dimension 16 in particular. At least nobody seems to think it should. And that's very confusing to me, but yeah, it's sort of not expected to work in dimension 16.
So I think, if my memory serves me correctly, then all the ones I mentioned are even and unimodular. And I think, as I say, one of the ones in 16 dimensions is just E8 plus E8, and one of the ones in 24 is E8 plus E8 plus E8. And I think it's not going to be trivial to work out the packing density of, say, E8 plus E8 plus E8 is probably just the cube of E8.
That you can do, yeah. You can work out the packing density from that because E8 has this sort of nicely spaced points.
Well, if it's just 3 copies of E8, I would have thought it was just the cube of the density.
I would say that is very likely, but I can't compute in my head, so I won't guarantee it. But yes, that seems like this.
I mean, without going into it, one might wonder if all those even unimodular 24-dimensional lattices had the same packing density. But that's easily checked, I think, with three copies of E8, and so that's probably well known. Yeah,
that actually should be checkable if it has the same density as each lattice.
So almost
and I'm pretty that it's almost certainly not as dense.
Yeah. Okay, thank you.
Welcome.
Right, thank you. So I had a question as well, Marcy. Are packings known in other dimensions that are believed to be near perfect or dense, near dense, but there is no proof?
No, not that I'm aware of. So there's a lot of things that there are packings in other dimensions that are like irregular. So where you take different sizes of spheres and pack. And those are thought to be sort of the densest possible packings in, say, I think there's one in 26 and a few higher dimensional ones. But I don't think there are packings outside of these that people expect to be perfect.
Right. So actually, I noticed that Nalin has typed in his question whether the topological group here considered is also compact.
No, not necessarily.
So another question I had is, you used the example of classical bits and information. If we go to quantum information, do you think that what is the corresponding mathematics behind that?
Oh, that's a really good question. Yeah, so in that case, right, your bits would be more probability states, right, in the quantum idea, and then you would need some type of spheres or way of checking error within probability. So I actually did see while preparing this talk, there are some people thinking about what is the equivalent of error correcting code in the quantum computing realm. I'm not sure if there's a consensus on that, but certainly you would need to, instead of having like 0, right, we need to have some probability state of something being at 0. So you would need either more dimensions or a way or some kind of really clever metric, I guess, on like determining when something is. I actually don't know. Are there metrics, Jan, for probability states?
Well, in quantum, you're talking about amplitudes, right? These are complex
Yeah,
valued, so it's not really probability. You don't have positivity necessarily, so it gets complicated. I don't know.
But yeah, I did see that there are some people, or at least there's a group of people who are thinking about this in the UK and had some interesting ideas about it. But
Sure.
There's not such a well-developed theory yet. But if somebody knows about that, I would like to know, because I only like saw the few articles on it.
Okay, so are there any further questions, people in the audience? If you put your Zoom hand up or type a question in Q&A. If not, Marcy, this was very entertaining, and I learned why sphere packing is related to deep space communication. So thanks very much for telling us about that. And to the audience, we hope to see you again in National Science Week next year, and we'll have another public lecture hosted by Matrix. Until then, I hope you enjoy the rest of National Science Week, and thank Marcy for a beautiful talk.
Thanks everyone for coming.